The series in example 2 is called the p-series. It is important in the rest of this chapter, so we summarize the results of example 2 for future reference as follows. So for theorem 1, the p-series of 1 over n of the p as n is equal to 1 to infinity is convergent if p is greater than 1, and it's divergent if p is less than or equal to 1. So for instance, the following series 1 over n cubed as n is equal to 1 to infinity is equal to 1 over 1 cubed plus 1 over 2 cubed and so forth. It's convergent because it is a p-series with p is equal to 3, which is greater than 1. But the following series of 1 over n to the 1/3 power, which is the same thing as 1 over the cube root of n, is equal to 1 plus 1 over the cube root of 2 plus 1 over the cube root of 3, is divergent because it is a p-series with p is equal to 1/3, which is less than 1. Now, testing by comparing. Now, the series 1 over 2 to the n plus 1 reminds us of the series 1 over 2 to the n, which is a geometric series with a is equal to 1/2 and r is equal to 1/2, and is therefore convergent. Because the series in number 2 is so similar to a convergent series, then we have the feeling that it too must be convergent. Indeed it is. So the inequality 1 over 2 to the n plus 1 is less than 1 over 2 to the n, shows that our given series in number 2 has smaller terms than those of the geometric series, and therefore all its partial sums are also smaller than 1, which is the sum of the geometric series. This means that its partial sums form a bounded increasing sequence, which is convergent. And it also follows that the sum of the series is less than the sum of the geometric series. So the series 1 over 2 to the n plus 1 is less than 1. Now, similar reasoning can be used to prove the following test, which applies only to series whose terms are positive. The first part says that if we have a series whose terms are smaller than those of a known convergent series, then our series is also convergent. The second part says that if we start with a series whose terms are larger than those of a known divergent series, then it too is divergent. So using the comparison test of these two series are series with positive terms. So again, if this series is convergent and we see that this series is less than or equal to the second series for all n, then we can say that this series is also convergent, and likewise with the divergence. Now, in using the comparison test, we must of course have some known series for the purpose of comparison. Most of the time we use one of these series: a p-series, where it converges if p is greater than 1 and diverges if p is less than or equal to 1, and a geometric series, where r to the n minus 1 converges if the absolute value of r is less than 1 and diverges if the absolute value of r is greater than or equal to 1.